How can we make deep reinforcement learning models interpretable? Imagine trying to understand how a robot decides to turn left or right in a busy street. Deep reinforcement learning models are like that robot, powerful but often hard to read. They learn by trial and error, making decisions based on complex calculations. This makes them seem like black boxes to us. But making these models understandable is key, especially when they are used in safety-critical areas like self-driving cars or medical diagnosis. So, how do we do that? First, we need to distinguish between explainability and interpretability. Explainability gives us insights into specific decisions after the model is trained. Think of it as a detective explaining one case. Interpretability, on the other hand, means designing the model so we can see how it makes decisions overall. It's like building a machine with transparent gears. One way to explain deep reinforcement learning models is through model-agnostic methods. These techniques work on any model without changing its structure. For example, Shapley values, borrowed from game theory, assign importance scores to features influencing decisions. This helps us see which parts of the input data are most influential across different situations. Tools like local interpretable model-agnostic explanations and Shapley additive explanations approximate how the model makes choices locally, giving us clearer insights. Another approach is to build models that are inherently interpretable. Instead of trying to explain a complex model afterward, we design models that are simple by nature. Prototype-based networks are a good example. They use familiar examples or prototypes to make decisions. For instance, an agent might decide to turn left because it recognizes a specific obstacle similar to a known prototype. This makes the reasoning process more understandable without losing performance. Self-interpretable models take this further. They replace the original decision-making process with simpler models that are easy to understand. These models can highlight important moments or features that led to a decision, like pointing out the critical step in a sequence of actions. This helps us see what really influenced the agent's choices. In environments with visual inputs, attribution techniques are useful. They analyze which parts of an image or scene the model focuses on. For example, in a game, these methods can show which objects or areas influence the model's action. This is especially helpful for understanding how visual cues affect decision-making. Reward decomposition is another method. It breaks down the reward signals into smaller, meaningful parts. This helps explain why an agent took a certain action based on immediate rewards or long-term gains. It makes the decision process more transparent. Finally, ethical considerations are important. In safety-critical applications, understanding why a model made a decision can prevent accidents and build trust. For example, if a self-driving car changes lanes, knowing why it did so helps us ensure it's making safe choices. Even in tools like ChatGPT or DALL-E, understanding how outputs are generated can improve transparency and user trust. In summary, making deep reinforcement learning models understandable involves using explanation tools like Shapley values, designing models with built-in transparency, highlighting important features, and breaking down rewards. These methods help us see how decisions are made, making AI safer, more trustworthy, and easier to work with in real-world situations.